The Doom gameplay you see on this screen is not rendering polygons. There is no underlying code calculating enemy health, player position, or bullet trajectories. The game engine has been completely removed, and an AI model is simply hallucinating the entire experience, pixel by pixel, in real time. For decades, interactive simulation has relied on programmatic engines. A CPU reads thousands of lines of explicit logic, calculates physics rules, and passes that geometry to a GPU to draw the frame. This animated diagram illustrates the departure from that standard. On the left, the traditional pipeline explicitly calculates and renders 3D space. On the right, GameNGen bypasses logic entirely. A neural network probabilistically guesses the next screen of pixels based solely on current pixels and user input. It performs this interactively, generating visual responses at 20 frames per second on a single tensor processing unit. This system was built by researchers Dani Walewski, Yaniv Leviathan, Moab Arar, and Shlomi Fruchter in a paper titled GameNGen. To understand how they achieved this, we have to look at the two distinct phases of their pipeline: how they built an exhaustive reinforcement learning dataset, and how they modified a latent diffusion model to process that data. This architecture demonstrates that the probabilistic logic used for static image generation can be extended to maintain high-horizon, interactive environments that respond to user agency. Training an autoregressive model to simulate a world requires a massive dataset. The model needs millions of examples mapping specific user inputs to precise changes on the screen. You might assume the easiest way to gather this data is to record humans playing the game. But human data is mathematically flawed. Humans play too optimally. We avoid walking into walls, we try not to die, and we stick to the main path. That leaves massive blind spots in the training data. A robust model requires comprehensive state action space exploration. It has to know exactly what the screen looks like when a player acts erratically, fires at empty corners, or takes damage. Think of it like mapping a cave. A human explorer takes one safe, efficient path to the end, ignoring the rest. But a mechanical drone bumping into every wall and sweeping every corner builds a complete, exhaustive map of the entire grid. To map the grid of Doom, the researchers deployed Phase 1 of GameNGen, a reinforcement learning, or RL agent, deployed to play the game continuously, making every possible move. This flowchart maps the exact outputs captured. We see the current screen pixels feeding into the RL agent. The agent decides on a keyboard action, instantly generating the next screen pixels. The system captures this sequence over and over, recording millions of trajectories. By forcing the agent into every conceivable state, including mistakes, deaths, and edge cases, the researchers generated a mathematically complete dataset. Without this exhaustive mapping, the generative model would have zero foundational data for what happens when a player inevitably strays from the optimal path. With the dataset built, Phase 2 transitions from data collection to active prediction, calculating the very next visual frame. The core architecture handling this is a latent diffusion model running through a U-net structure, similar to the technology behind text-to-image generators, but optimized for continuous sequential output. This U-net diagram illustrates the precise input mechanism. A sequence of past visual frames and a tensor containing the player's current keystroke action are merged directly into the central latent space. Inside that latent space, the model performs a denoising process. It starts with pure Gaussian noise and iteratively subtracts that noise until a clean Doom frame emerges, guided explicitly by those past frames and the current action data. For the simulation to be playable, this denoising process must happen rapidly. The researchers optimized the inference steps so the model completes this entire cycle 20 times per second, ensuring real-time interactivity. A standard diffusion model struggles with fine, granular details. To fix this, they applied decoder fine-tuning, forcing the model to heavily penalize errors in sharp features, like the text on the UI or the digits on the player's health bar. The result is a U-net architecture that successfully compresses thousands of lines of rigid rendering code into a single, highly accurate, real-time probabilistic guess. But predicting a single frame is only half the problem. Sustaining those predictions over thousands of frames introduces the primary enemy of video generation, autoregressive drift. In machine learning, exposure bias occurs when a model is trained exclusively on perfect ground truth sequences. During live inference, the model will inevitably make a tiny mistake. Because it has never seen a mistake during training, it doesn't know how to correct it. Consider a tightrope walker trained only in a perfectly still room. They execute every step flawlessly, but facing a minor perturbation, a slight gust of wind, they lack the recovery skills to regain their center of gravity, and they collapse. Mathematically, this means a microscopic 0.1% error in frame 1 compounds into a 1% error in frame 10, leading to total structural collapse into noise by frame 100. This line graph shows the solution to that collapse, a technique called conditioning augmentations. Notice the standard model crashing toward zero. Beside it, the GameNGen model maintains perfect stability across thousands of frames. They achieved this stable line by deliberately injecting calculated Gaussian noise into the past conditioning frames during the training phase. They intentionally corrupted the data. By forcing the model to predict the next clean frame from a slightly corrupted past frame, the network learned error correction vectors. It learned how to continuously pull drifting, noisy states back to the true data manifold. Equipping the model with this forced self-correction mechanism mathematically prevents exposure bias, allowing the simulation to remain stable indefinitely. This bar chart measures output fidelity using peak signal-to-noise ratio. Beside the ground truth doom baseline, GameNGen achieves a 29.4 PSNR. Contextually, this score is equivalent to the visual degradation of a standard lossy JPEG compression. Structural integrity is preserved. To test this qualitatively, the researchers subjected the output to a Turing test for human raters. Raters were shown short clips of the actual game and clips of the GameNGen simulation and asked to identify the AI. Even after the simulation had been running auto-regressively for 5 continuous minutes, the raters performed only slightly better than random chance. Prior state-of-the-art video generation models struggle to maintain temporal consistency for more than a few seconds before characters mutate or backgrounds dissolve. Sustaining a 29.4 PSNR and fooling human raters for 5 continuous minutes validates neural video generation as a mathematically viable method for sustained interactive simulation. The architecture does have strict limitations. It operates within a fixed context window. The model only conditions its generation on a little over 3 seconds of past frames. If the player opens a door, leaves the room, and returns 3 minutes later, the model has no memory of the door's state. It will probabilistically guess whether the door is open or closed based purely on the immediate context. Furthermore, calculating a diffusion process 20 times a second demands severe computational overhead. Running this engine requires high-end TPU infrastructure, currently inaccessible for consumer hardware. Despite these constraints, the mechanics demonstrated here, using RL agents for exhaustive mapping, replacing explicit physics with latent diffusion, and deploying conditioning augmentations to eradicate autoregressive drift, form a complete blueprint for neural simulation. Today, the model is hallucinating doom. But as hardware scales, this exact architecture is positioned to ingest real-world autonomous driving datasets, or the dense physics calculations of Unreal Engine 5, replacing rigid programmatic rules with fluid probabilistic world models. To keep tracking the architectures driving these breakthroughs, hit the like button, subscribe to Gradient Daily, and ring the bell to never miss a paper.